The work was done by QUIINN, who is the first author, and we are talking about the investigations we have done to develop a CO2 refrigeration unit. After an introduction and giving some background information, I will explain the challenges of to do the development, the experimental setup in the laboratory. I will show you the results, and I will conclude the presentation and show you in the last slides the final design of the unit. What are the market drivers and trends in Europe? So we have increasing demand for low GWP solutions in Europe. We have the F-gas regulation, we have taxes and subsidiary schemes. We have the Lot 1 to set the minimum efficiency requirements, which gives a benefit. If you have a system with a lower GWP of 150, you get 10 to 15% credit for this. There are technology trends which need to be considered for new development, like capacity modulation by inverter, electric commutated fans, advanced controls, communication, heat recovery, electronic protection, diagnostic and remote monitoring. And you see here on the map, some countries in the northern part of Europe, they have already taxes. Denmark, even Spain has tax. France is considering this. But there's also some countries in Europe who give incentives for new technology. Germany, Belgium, Switzerland, Austria. So they take part of the cost when you make the system with low GWP alternatives. I think you have seen this many times, the F-gas regulation, the phase down on the CO2 equivalent up to 21% at the end of 2030. We are now already here in the second phase with a reduction of 63%. And as a consequence, the HFC prices grow dramatically. This slide is a little bit outdated. We are above here, we are already 800, 900% price increase so far. When we look to the future technology in the commercial refrigeration sector, especially in the food sector in supermarkets and smaller shops, we see that big hypermarkets will definitely go to centralized CO2 systems and booster systems, maybe cascade systems, maybe even using HFOs on a high side to compensate for warm climates. Supermarkets up to 2,500 square meter, basically CO2 booster system, cascade systems, or distributed HFO or CO2 system, and this type of equipment is a topic of my presentation. In small supermarkets you find also some racks, these smaller units, or integrated display cabinets, which you find in hard discounter more and more, and smaller systems. They have smaller condensing units, also going more and more into propane. You find also some very small HFO and CO2 units now, or display cabinets with integrated refrigeration system. And for the cold room, you have also equivalent equipment. This paper shows you, or will talk about the experimental study we have performed to develop our CO2 unit. And this investigation was done in parallel with the design of the system, the product development phase. And the aim was to investigate different technologies and potential improvement with respect to the CO2 refrigeration system. The final unit design incorporates a bypass cycle, and we will discuss more in detail in the coming slides what is the impact on this. And this study was for us very important to understand what capacity and performance the system can be delivered. Furthermore, we run experimental and numerical simulations to improve the system performance, and we did practical implementation for a medium temperature CO2 unit, transcritical, and look for the different challenges and limitations when we are using CO2 as a working fluid. And also one target is also when you are looking to warm climates, the system has to operate at warm ambient conditions. And we developed the software tools, so you can download this from the Emerson website to select your CO2 unit. We are looking into these different types of cycles: the fleš-gas bypass cycle, with or without internal heat exchanger, multi-ejector cycle, mechanical subcooling cycle, parallel compression, EDI cycle, expander cycles. And we decided we have to select the most promising in respect of cost, technology, availability of components for the main unit to basically increase the ambient temperature operating range for these units and increase the potential target market for these units. And of course increase the performance of the systems. So all these cycles which I mentioned here at the top, we investigated in the first step theoretically. So this slide, a little bit busy, but it shows you the different cycles we looked for. It shows the cycle in the pH diagram, and you will find all this information in the proceedings, of course. And in this table you see the COP of the system at different ambient conditions from 10, 20, 25, and 35 degrees. And in the last column, the seasonal performance of the system for a specific climate condition. In this case, it is Strasbourg climate condition, which is used in the EU. The first cycle is a basic cycle, which was become more popular due to Professor Lorentzen from Norway, introducing the high pressure control. And this cycle gives you a seasonal performance about 3, and it's considered to be the basic cycle for all the comparisons. The next cycle is already the cycle with a flash tank, and the flash tank is controlled with a bypass valve, which brings the gas from the flash tank directly to the compressor and doesn't, so it's bypassing basically the evaporator. That is this cycle you see here. This line is the flash tank pressure of the system, which is controlled. This gives you a very similar performance compared with the basic cycle. In reality, there is a small impact because the amount of flash gas passing the evaporator has an impact on the evaporator heat transfer efficiency. This cycle here is the multi-ejector cycle, which uses the high pressure gas in an ejector to pump up gas to the flash tank. This cycle has again an 11% improvement compared with the basic cycle. This cycle number 6 is a standard cycle. Oh no, this is not a standard cycle. This is a cycle we are talking also with a mechanical subcooling. So at the end of the flash tank, on this point, we have a mechanical subcooler which reduces the temperature of the gas cooler outlet at the same pressure. And this gives you also in a seasonal performance calculation 7% benefit gain. This cycle is a standard cycle with parallel compression, very often used in compressor racks today, especially important for warm climates. And this cycle is a so-called EDI cycle, where you use a compressor, for example a screw compressor, and you inject the flash tank directly into the compressor, into the second stage. And the last cycle is an expander cycle, and which gives you also quite reasonable performance increase. And when we look to the top performer, EDI cycle 22%, expander cycle 40%, multi-ejector 11%, and mechanical subcooling 7% performance improvement. But there are some limiting factors, which are footprint, there's not enough space in these components, complexity, cost, and of course available technology. What are the challenges? This graph, this pH diagram, shows when these 2 points here at the corner are on an isotherm, on the same temperature basically. When you increase the pressure, you gain enthalpy, and this was the idea of Professor Lorentzen. But the optimum high pressure, which you theoretically can achieve, has to be also be delivered by the compressor, and in this case this blue point here is already out of the compressor envelope. So what theoretically can be done, not necessarily can be achieved due to compressor limitations. In our design we selected the flash tank with a 90 bar, and we can operate the flash tank with a safety limit of 85 bar. And this time, at this point, the system stops, and this is roughly already at 35 degree ambient, or 36, and this temperature is, for our climates now, not high enough. So this summer, even in Germany, was up to 40 degrees, then the system would not work anymore. So we need to find a solution to extend the ambient temperature operation. We used for the testing our Aachen solution center, the test facilities. You see here one cold room climatic chamber. Here on the side is another climatic chamber. In the climatic chamber B, we put the evaporators, and here in this case air coolers. The unit is placed in chamber A, also with the mechanical subcooling, also in chamber A. The system is equipped in this box. This is the standard electronic of the unit. You have here the iPro rack controller. This is the inverter drive for the compressor, and these two controllers are the controllers for the high pressure valve and the flash tank bypass valve. On top, it's connected to an XWeb EVO 500 to bring the data directly into the internet. And on top, we have connected a national instrument system with a lot of sensors to monitor all the data of the system. Here again, the cycle. This is a standard cycle: compressor, gas cooler, high pressure control valve, and the flash tank. In this case, this high pressure control valve controls only the high pressure. The pressure in the flash tank is floating and depending on the amount of liquid refrigerant leaving to the evaporator. That is the standard cycle. The bypass cycle looks very similar, but here we have from the flash tank a line and another valve, that is a flash tank bypass valve, and this bypass valve keeps the flash tank pressure in a specific range. And the third cycle we investigated is a cycle with mechanical subcooling. So after the compressor and the gas cooler, where here is at the point 3 the high pressure valve and the high pressure control, we have a mechanical subcooling to further subcool the refrigerant to increase the enthalpy before throttling into the flash tank and to the evaporator. All in all, we investigated the system at 3 evaporating temperatures from -20 to 0, and at 3 speeds from 30 to 60 Hertz. So in total we had 36 test points. In these diagrams we try to show the COP of the system, which is the red line, and the blue line is the cooling capacity versus the operating conditions. And these dotted lines is the area of optimum high pressure, which is controlled by the iPro rack controller. And you see the maximum COP is perfect in the range of the controller. Here also with the bypass control, it's a little bit more sharp. And here with the mechanical subcooling, we can state that the iPro rack controller makes a very good job in adjusting the optimum high pressure to maximize COP and cooling capacity. Here are the results. I would say we should look just to the upper diagrams. The bottom diagrams are the operating conditions at different frequencies, at different operating temperatures for the basic cycle and the flash tank bypass cycle. And the upper dots here is the cooling capacity for the mechanical subcooling, and the same here is the COP for the system. And we can say that the capacity there's a small capacity reduction when we have the fleš-gas bypass cycle compared with the basic cycle, and we get a large increase of capacity when we have a mechanical subcooling for the system. When we look to the COP, there is a small reduction in COP with a bypass cycle in the order of 1%, and there's a large increase of COP when we have the mechanical subcooling, on average up to 18% better performance. Oops. Normally the high pressure control is done when you measure the pressure at the gas cooler outlet and to control the pressure in the gas cooler. And in this case we try something different. We reposition the sensor, the pressure sensor, after the subcooler. This is a test with a mechanical subcooling to look what the impact is on the behavior of the system when we do this, but we are just using the standard high pressure control mechanism. So basically the temperature and the pressure which is used for this high pressure control will be lower, and you see it in this diagram. This was the unit operation without mechanical subcooler, and then the mechanical subcooler was switched on and reduced the temperatures, and due to the algorithm of the iPro controller, also the high pressure is reduced by 12 bar. That means this allows the system to operate at higher ambient temperatures, extending the compressor envelope, and the flash tank pressure can still cause limitation with respect of ambient temperatures. That's another point. But we have also a significant reduction in the discharge line temperature of 16 Kelvin. This again allows us to achieve higher ambient operating conditions to extend the compressor envelope. In terms of gains of capacity and COP, we gain a little bit less COP improvements, just 7% and maybe 7% capacity and 2% COP. Nevertheless, we can improve with an optimum gas cooler algorithm need to be optimized. We can go for higher ambient temperature with the system. This diagram shows the experimental results for the so-called SEPR calculation. In the SEPR calculation, which is specified in the lot 1, you calculate the performance at 4 different ambient conditions, at 5 degrees, 15 degrees, 25 and 32 degrees. And you see the compressor capacity is modulating. So 32 degrees is the design point where the system runs at maximum speed at 60 Hertz at an evaporating temperature of -10. And this gives us a COP of 139. In the other temperatures, the capacity is modulated to go down to 80% cooling capacity. And this results then here in equivalent COPs, and the SEPR value is then calculated from the single COPs using a formula. So the conventional cycle delivers an SEPR of about 3.02, bypass cycle through, which is a loss of 1%. The mechanical subcooling delivers a value of 3.34, performance boost of 11% when we compare it with the basic cycle. And the capacity data for each cycle of the design point is also displayed. So this nearly 18 kilowatt is a conventional cycle, 16.5 bypass cycle, the reduction of 6% in capacity, and 23.7 for the mechanical subcooling cycle, it's a boost of 34%. Test data is shown in the table for the bypass cycle, and the SEPR from the test data was calculated at 2.97 theoretically, which is in percent, 1% of the calculated value. So why a bypass cycle? It slightly reduces the seasonal performance a little bit by 1%, but it provides 6% reduction in capacity also. So why doing this? There's some reason behind it. It can operate at higher ambient conditions, at excess of 42 degrees versus 35 degrees, and it allows a full control over the liquid pressure and therefore the liquid line pressure. In this case, the system can be assembled with standard copper pipes and use lower pressure cooling evaporators in the supermarket. installation is less complex and technically less challenging, and it's a low-cost, simple cycle, as you see here in the schematic diagram. So conclusion, each configuration, conventional cycle, bypass cycle, mechanical subcooling cycle, have been tested and modeled for performance evaluation and comparison. Respect to the conventional cycle, the bypass cycle, loss of term delivered capacity and COP in region between 3 and 1%. And the mechanical subcooling cycle represented a capacity and COP improvement of 30% and 80% respectively. But this is, of course, additional investment and would make only sense in extreme climates. The models were generated to develop selection and analysis tool, which we incorporated within the Emerson selection software. So we have validated this and calculated seasonal performance. This unit is the first CO2 unit which is ASACOM certified by the ASACOM certification scheme, and the SAPR of the bypass cycle was calculated with test data, with very good agreement, and yeah. And here I show you some pictures of the system. So what we have today, we have here the CO2 unit with a controller, supervisor controller. These units are multiple units serving the cooling requirements. Instead of having one big refrigeration system, we have several units connected. This brings us greater flexibility, extending the system capacity. We have lower leakage rate due to smaller system size and wider change of refrigerants. So these units will be also available with HFO refrigerants. You see here the range of equipment from very small equipment up to the discounter supermarket, what we produce. And this is here the specific CO2 unit. It has an integrated inverter modulation from 25 to 60 Hertz. It's a high pressure oil level controller, pressure rating 90 bar liquid line, 120 bar discharge, 90 bar suction, electronic commuted fans, liquid receiver, external main off switch, and you can have a visual inspection of liquid level inside the side glass, and there are options for heat recovery if you would use the waste heat from the system. And here are the 3 models we have placed in the market so far. Yeah, thank you for your attention, and if you have any question, I'm pleased to answer this. Thank you very much.